Okay, class, here are the videos for related rates. So if you want to rewatch how we did these, we are going to make sure we use implicit differentiation throughout this process. So here are the steps for doing related rates problems. Make sure to always draw a picture. It's always going to help out with what's happening. We're going to label everything. And the most important part is this find when given section. That's going to help us with a guide as to what we're looking for, what information we have, and hopefully how to solve this. And remember, a lot of this does use geometric shapes. So let's take a look at this problem. A rocket is rising vertically and is tracked by a radar station on the ground 5 miles from the launch pad. So here's my rocket, and let's go ahead and draw a little launch pad right here. So this is where that rocket is launching off of. So our rocket hasn't launched yet, so let's start right here. It's also telling me that there is a radar station somewhere. So let's draw a radar station here. And just for, for fun, let's put antennas here to show that it's a radar station, right? Okay, so if I take a look at this picture, it's saying a rocket is rising vertically and is tracked by a radar station. So I know this rocket, all it's going to do is go up vertically, right? It's tracked by a radar station that is 5 miles from the ground, from the launch pad. So what I do know is this distance right here is 5 miles. Okay? It says, how fast is the rocket rising when it is 4 miles high? So what I'm looking for is when this is 4 miles high, and its distance from the radar station is increasing at a rate of 2,000 miles per hour. So if you notice, this says it's a rate. Since it's a rate, I know this is equal to a derivative of something. Let's undo that writing. This is equal to some kind of derivative. And specifically, it's the distance from the radar station to where the rocket is. So if here's the radar station and there's the rocket, that means this distance, let's call it z, is dz dt equal to 2,000. So just to call this z, why don't we call this one x? And why don't we call this one y? Okay. So what shape do you see in this picture? Good, you see a triangle. And let's take a look at some of the triangle equations we know from geometry. Well, if you take a look at this one, specifically, this is a right triangle. So I know, why don't we use Pythagorean theorem, x squared plus y squared equals z squared, to find these different pieces. So let's find out what we're looking for. I'm going to write find when given here. Find when and given. So it says, how fast is the rocket rising? So I'm looking for how fast it's rising. Well, if I'm looking for how fast this is going, that's going to be my dy dt. I'm trying to find out how fast is y changing. When it is 4 miles high, so I need it when y is equal to 4. And its distance from the ground is this rate. So given dz dt equals 2,000. So our next step is to take the derivative. So let's take this derivative. I'm going to get 2y dy dt. Oh, I forgot the x. 2x dx dt equals 2z dz dt. So let's plug everything in and see if we're missing anything. I'm going to get 2 times my x is 5. Now I have a dx dt. Well, is this launch pad moving distance from this radar station? No, so since it's set and it's at rest, I know that's equal to 0. Plus 2 times my y is 4. My dy dt is what I'm looking for. Let me shift all of this over. And so if I continue this, I get equals 2z. dz dt is 2000. Now the problem is that I'm missing this z. So how could I find that? Well, I could find it by using the original equation. So let's go ahead and use the original equation to do this. We know x squared plus y squared is equal to z squared. So if I plug everything in, I get 5 squared plus 4 squared equals z squared. That gives me 25 plus 16 is equal to z squared. And if I add those up, 25 plus 16 gives me 41. So z is equal to square root of that, so z is equal to radical 41. So let's go ahead and take these numbers right here and plug everything in into the right spots. Let's get these together. Okay. Slide this to come over. So let's rewrite this so it's a little neater. If I plug everything in, I get 2 times 5 times 0, I'm just rewriting this, plus 2 times 4 dy dt is equal to 2 radical 41 times 2000. So if I solve for this, this cancels, and I get 8 dy dt is equal to 4,000 radical 41. And I need to divide by 8. This cancels dy dt. If I were to cancel this, I get 500. So it's equal to 500 radical 41. And I need to do my units. So these are in miles per hour. Okay. So this rocket is rising upwards at 500 radical 41 miles per hour. Okay, let's take a look at the next problem. It's another triangle problem, and let's see if I use the same information. It says the height of a triangle is decreasing at a rate of 1 centimeter per minute, while the area is increasing at a rate of 2 centimeters squared per minute. At what rate is the base of the triangle changing when the height is 10 centimeters and the area is 100 centimeters cubed? So what you notice is we have this triangle, and I'll put it up here, but what's happening is this triangle has a base, the height is decreasing, so it's getting, the height's getting smaller. So let's label some of these. It says the height is decreasing. So I know the rate of the height is decreasing, so let's call it dh dt. It's decreasing, so that's a -1. It says the area though, so dA dt is increasing at 2 centimeters squared per minute. It says at what rate is the base of the triangle changing? So I'm looking for the base. I'm looking for dB dt when the height is 10 centimeters. So I know the height is 10 centimeters and the area is 100. So let's figure out what equation deals with area, a base, and a height. Well, you should say area is equal to 1/2 the base times the height. Let's do our find when given. Find when given. So it says, at what rate is the base of the triangle changing? So we actually labeled this right here. I need to know when the base is changing. And it says when the height is equal to 10. So know, oops, I want to do this when the height is equal to 10, given all this information right here. And this right here. So all of this information is going to give us an answer to this problem. So let me fit all of these here in the corner. Let's go ahead and take this derivative. So if you notice, I have a first term and a second term. So dA dt is equal to the first term times the derivative of the second, plus the second term times the derivative of the first, dB dt. So let's plug all our information in. I know dA dt is equal to 2, 1/2. I don't have a base right now. I do know the height is decreasing at -1, plus 1/2. My height is 10, and I'm looking for dB dt. So I can't finish solving this till I get a b. So where can I find the b? Well, I can do that with the original equation. So my area is supposed to be 100, and I know my height is supposed to be 10. So if I do that work, this becomes a 5. If I divide by 5, b has to equal 20. So I'm going to plug that into here. 1/2 times 20 times -1 plus 1/2 times 10 dB dt. And if I scroll down to make some space, all we do is a little bit of algebra. Get 2 is equal to, that becomes a 10, so -10 plus 5 dB dt. Move everything over, I get 12 plus 5 dB, 12 equals, 12 is equal to 5 dB dt. If I divide by 5, then I get that the base is changing at 12 over 5, and my units here are centimeters per minute. So let's do one last problem with related rates. It's a little bit more difficult. It says, let's see, let me make sure I give you guys enough room for this. This says a tank in the shape of a right circular cone, so here's a right circular cone, is being filled with water. So what I know is that water is coming into here at 13 feet cubed per minute. But I also know water is dripping out of here at 1 foot per minute, so that's a -1 foot per minute. The tank has a height of 30 feet, so I know if I take a look at the tank, this height is 30 feet, and it has a radius of 15 feet. 15 is equal to R. In order to collect the water that leaks out of the tank, a barrel in the shape of right circular cylinder is placed below the leak. The barrel has a height of 5 feet. So this barrel right here has a height of 5 feet. And it has a radius of 3 feet. So that's some of the information we've gathered. So let's go ahead and take a look at the first problem. And let's go ahead and copy this picture. Alright. So if I move this down, it says write an expression for the rate of change of the depth of the water at the center of the cone in terms of the depth. So for this section, all I really need is this part of the graph. So let me just plug in my technology real quickly. Okay, so as we're doing this, I want to know this depth. Well, the equation that would help us is to find out how much water this cone is holding. And so from chemistry, we remember that's equal to the volume. So what I have here is the volume is equal to 1/3 pi r squared h. And so the nice thing about this is I could use ratios to kind of work out these different numbers. So I'm going to create a ratio up here that the radius is 15 and the height is 30. Let's cross multiply and I get 15h is equal to 30r. Now what I want to do is I want to get rid of this r because I don't want to have to work with too many variables. So if I get rid of that, I see that r is equal to h over 2. So what I'm going to do is plug this into here. And what we get is volume is 1/3 pi h over 2 squared h. If I simplify that, I get 1/3 pi h cubed over 4. And if I simplify that again, I get 1 over 12 pi h cubed. So now instead of having 3 variables, what I have now is 2 different variables. So let's go ahead and find what I'm looking for. It says write an expression for the depth. So what I'm looking for is I want to find dH dt. So let's go ahead and do this. And if I take this derivative, I get dV dt is equal to 3 over 12 pi h squared dH dt. Okay. And so what I'm going to do is take a look at my dV dt. Well, if this was going in at a rate of 13 but coming out at a rate of 1, that's going to give me 12. 3 over 12 pi my h is always changing. So what I'm going to do now is just solve for this dH dt. And what I get is this will become a 1 over 4. So if I move everything over, I get 48 over pi h squared is equal to dH dt. Alright, let's take a look at the next piece of this. And once again, let us put in the picture. Alright, it says find the rate of the depth of the water in the cylinder. So now what I'm looking at is this section right here. So same thing, I need the volume of a cylinder. So the volume is equal to pi r squared h. Now here's the difference. In the picture of the cone, as the water level decreases, right? Don't you see that the height and the radius changes? Whereas here, as the water level decreases, only the height changes. The radius is still a 3 since it is a right circular cylinder. So what we're going to do is I'm going to plug in 3 since I know that this is not changing. So this gives me 9 pi h. Now we can take the derivative of this and I get dV dt is equal to 9 pi dH dt. The water was leaking at a rate of 1. That means it's also entering at a rate of 1. So I get 1 is equal to 9 pi dH dt. And in order to get my dH dt by itself, I divide by 9 pi. So dH dt for the cylinder is 1 over 9 pi. And my units here are feet per minute. That's the end of related rates part 1. We'll take a look at related rates in a couple of lessons later on. Okay, thank you.